Have you ever had a day so perfectly aligned it felt scripted by an unseen hand? A last-minute decision to take a different route to work leads you to bump into an old friend who has the perfect job opening. A coin seems to land on heads just when you need it most. A sudden impulse to call a relative reveals they were just about to reach out to you with important news. These moments of serendipity, these streaks of what we call luck, often feel too meaningful to be mere coincidence. We instinctively search for an explanation, a hidden layer of causality beneath the surface of random chance. It is a profoundly human impulse to wonder if there is a deeper order to the universe that occasionally peeks through, arranging events in our favor. This feeling leads us to a fascinating, if speculative, question that sits at the very edge of scientific inquiry. Could the strange and counterintuitive rules that govern the universe at its smallest scales be responsible for these large-scale lucky breaks? The world of quantum physics, with its inherent uncertainties, bizarre connections, offers a tantalizing toolbox of concepts that seem to echo our experiences with luck. To understand the potential link between physics and luck, we must first journey into the microscopic realm of quantum mechanics. This is the science that describes the behavior of atoms, electrons, photons, and other fundamental particles. Down at this level, the world operates by rules that defy our everyday intuition. One of the most foundational principles is called quantum indeterminacy. Unlike a thrown baseball, whose future position and speed can be calculated precisely if we know its starting conditions, a quantum particle exists in a cloud of possibilities. An electron, for instance, does not have a single, definite location until it is measured. Instead, it exists in a superposition of many possible locations at once, each with a certain probability. We can calculate the odds with stunning accuracy. For example, there might be a 40% chance the particle will be found here, and a 60% chance it will be found there. But we can never predict the exact outcome of a single event. This inherent randomness is a feature of reality itself, a fundamental fuzziness that cannot be engineered away. It is this core concept that opens the door, however slightly, to speculations about luck. Another strange and captivating feature of quantum mechanics that gets woven into discussions of luck is entanglement. Albert Einstein famously called it spooky action at a distance, and for good reason. When two particles are created in a special linked state, they become entangled. This means their properties are correlated in a way that defies classical explanation. For example, if you measure a property like the spin of one particle, you will instantly know the spin of the other, no matter how far apart they are, in the same room, on opposite sides of the galaxy. It is as if they are a single system, communicating faster than the speed of light. This instantaneous correlation is not communication in the traditional sense. You cannot use it to send a message. However, its mysterious nature has led to some wild and imaginative speculation. If particles can be linked in this profound, non-local way, could larger systems also share some form of entanglement? Could a person, composed of countless particles, be entangled with a particular set of events, or even another person? The idea is poetically attractive, sounding like a physical basis for concepts like fate, destiny, a deep connection between soulmates. It suggests that your own state could somehow be correlated with the outcome of an event happening elsewhere, creating a form of luck that is written into the fabric of reality. While quantum indeterminacy and entanglement offer tantalizing possibilities, nature has a powerful mechanism that acts as a strict gatekeeper, preventing these strange quantum effects from leaking into our everyday world. This mechanism is called decoherence. Decoherence is the process by which a quantum system loses its quantum properties. Superposition. Entanglement. A single quantum particle needs perfect isolation. It bumps into an air molecule. It gets hit by a photon of light. It feels a vibration of heat. The cloud of possibilities collapses into a single, definite, classical state. Think of a coin flip. A coin is macroscopic, trillions of atoms. As it tumbles through the air, it interacts with the environment. It collides with billions of air molecules every microsecond. It is bombarded by photons from ambient light. Its internal atoms vibrate with thermal energy. Each interaction acts as a tiny measurement, forcing classical states. Any fleeting superposition is washed out with incredible speed, long before it could affect heads or tails. This is the main objection to quantum-governed luck. The macroscopic world is just too big, too warm, too noisy. An entangled pair is like two musicians in a soundproof duet. Decoherence is the doors opening and a stampeding herd rushing through. The duet is lost. Even without invoking the mysteries of quantum mechanics, classical physics offers a powerful explanation for why the world so often appears random and unpredictable. This explanation is found in chaos theory. Chaos theory is the study of systems that are highly sensitive to their initial conditions. In such systems, a minuscule, almost immeasurable difference in the starting point can lead to wildly different outcomes over time. The most famous metaphor for this is the butterfly effect. The idea that the gentle flap of a butterfly's wings in Brazil could, in theory, set off a chain of atmospheric events that ultimately results in a tornado in Texas. This is not a quantum effect. It is a feature of large, complex, classical systems. A coin flip is a perfect everyday example of a chaotic system. The final outcome, heads or tails, is exquisitely sensitive to a host of tiny variables at the moment of the toss. A fractional change in the upward force applied by your thumb, a minute difference in the spin rate, a slight variation in the point of impact on your skin, tiny fluctuations in the air currents in the room can be the deciding factor. These are not quantum uncertainties. They are definite, classical properties. The problem is that they are far too small and numerous for us to ever measure or control with perfect precision. This practical inability to know the starting conditions perfectly is what makes the outcome unpredictable for us. This concept of practical randomness is crucial. It shows that an event does not need to be fundamentally indeterminate at the quantum level to be unpredictable. The complexity of the classical world is more than sufficient to generate all the luck we experience. When we weigh the speculative allure of quantum luck against the hard evidence and established theories, the mainstream scientific consensus is clear and cautious. As of today, there is no credible scientific evidence or widely accepted theory to support the claim that quantum mechanical effects directly influence large-scale events in a way that we would perceive as luck. Physicists have confirmed the strangeness of quantum mechanics, indeterminacy, superposition, entanglement. However, the proposed leap from these microscopic behaviors to the macroscopic outcome of a coin flip, a lottery drawing, a chance meeting, is considered highly speculative and unsupported by data. The primary obstacle, as we have discussed, is decoherence. It is a formidable and fast-acting barrier. The speed at which a system's quantum nature is erased by environmental interaction is staggering, far shorter than any macroscopic event. For a quantum effect to steer your luck, it would require a novel mechanism, one currently unknown to physics, that could protect a quantum state from decoherence or allow it to influence a large system despite decoherence. Furthermore, science operates on the principle of parsimony, often called Occam's razor, which suggests that the simplest explanation that fits the facts is usually the best one. In the case of luck, classical explanations are far simpler and require no new physics. Decades of research, including studies by the Princeton Engineering Anomalies Research Lab, have failed to produce replicable, statistically significant results. While the scientific case is weak, it is a fascinating intellectual exercise to consider the implications if this speculative idea were ever proven true. What if we discovered a reliable mechanism by which quantum events could be guided, or their outcomes amplified, to shape macroscopic fortune? The consequences would be nothing short of revolutionary, shaking the foundations of science, technology, our very definition of what it means to be human. First, the field of statistics and probability would need a radical overhaul. If certain outcomes could be subtly biased by quantum effects, perhaps linked to human consciousness or other unknown variables, then our entire approach to prediction would be flawed. Second, physics itself would be turned on its head. The discovery of a mechanism that bypasses decoherence to link the quantum and classical worlds would be as significant as the discovery of quantum mechanics itself. engineers and technologists would race to harness this new principle. Could we build luck machines that nudge probabilities in our favor? Could we develop medical treatments that use focused intention to improve the quantum-level processes in our cells? Finally, our understanding of human meaning, consciousness, and free will would be transformed. While we remain far from this reality, imagining it shows the deep human desire to find meaning and connection in the cosmos. Before we go, huge thanks to Thunderbird Perch for making this video possible. If you enjoyed this, please subscribe, like, and share. Your support means everything. Think about it. A new world awaits.